Alright, so today we're going to start looking at dimensional analysis. And what dimensional analysis is a pretty darn powerful problem-solving tool. You analyze what dimensions you have. In other words, you take a look at the units you have, and then you try to figure out how to get the units you want. And you can do this to change unit systems. You can also do it if you want to determine any other quantity. If, say, you don't have an equation for it. If you know what units you have and what units you need, you can find a way to get the desired unit. So the key in any dimensional analysis problem is you have a given unit. These are the units that are given in the problem. And you want to find your desired unit. Now, what you have to do is you have to determine a conversion factor. What a conversion factor is it's going to change your unit system from your given unit to your desired unit. And you want to make sure that it's always multiplication and then followed by your given unit being on the bottom. Since multiplying by a fraction crosses out the given units, you end up with the desired unit. You'll also see as we go through these problems that this format, this whole format here, is a nice way to set up any of your dimensional analysis problems. It allows you to quickly and compactly explain your problem and to check and make sure that there are no errors by simply seeing if your units cancel out. So we're going to continually do all these problems following this format, and I highly suggest you start using this format in order to keep yourself on task. Alright, as I said, in dimensional analysis you have to have conversion factors. So here we have a series of conversion factors that you should know. We often do a lot of things in imperial measurements in the US, and all of the scientific things we're going to deal with is in metric. So going back and forth between the metric system and the imperial system is very, very important. Now, here we have these imperial to metric conversions. So 1 inch is equal to 2.54 centimeters, 1 liter is equal to 1.0567 quarts, 2.205 pounds equals 1 kilogram, and 1 pound is equal to 453.59 grams. I would know these. And then, oftentimes we're moving through the imperial system. Now, most everybody should be familiar with these guys. So, 12 inches is 1 foot, 5,280 feet is 1 mile, and so on and so forth. So these that allow you to move through the imperial system, if you don't already know them, I would know those as well. Other conversion factors can be used, they may come up, but all of these ones that are listed, both in the top and the bottom, should get you through 99.9% of any problem that you want to do, just simply by combining these conversion factors in a long string of dimensional analysis. Alright, so we're going to work through a series of example problems. Now, I would disregard the page numbers in the text and just follow along with the numbers of the problems. We're going to do number 40, 48, 50, 83, 91, and 103. And all of these problems come out of the 11th edition of Chang and Goldsby's Chemistry. So here we have problem number 40. And it asks us to carry out the following conversions: 242 pounds to milligrams, 68.3 cubic centimeters to cubic meters, and 7.2 meters cubed to liters, and finally 28.3 micrograms to pounds. So the first thing you'll notice that there's a lot of imperial to metric conversion going on. So we're going to need some of those conversion factors from that list that I showed you previously. So let's start off with A. So in A, we're looking to go 242 pounds to milligrams. I have no conversion factor that goes directly from pounds to milligrams, but what I do have is I have a conversion factor from grams to pounds. So I'm going to take what I know, the 242 pounds, and I'm going to use my gram to pound conversion factor, and I want to multiply by this fraction, and I want my given unit to be on the bottom. So pounds needs to be on the bottom, and grams needs to be on the top. Now, from that table, 1 pound is 453.59 grams. Now, you might be tempted to go ahead and do this piecemeal, but it really is a good idea to follow through and do this as one long string. So, I've got grams, but that's not my final answer. I want my final answer in milligrams. So, I'm going to go ahead and multiply by another conversion factor where milligrams is on the top and grams is on the bottom. So, milli means 1,000th, right? So, you could write it as 1 milligram is 1/1000th of a gram. But I tend to do this in terms of multiples, big numbers, always using a positive exponent. So 1 gram is 1,000 milligrams. And so to do this, you take the number you have times the top divided by the bottom, times the top divided by the bottom, so on and so forth. So when we do this, we get 109.768780. Now, from our sig figs, we know that that's not going to fly. We should have only 3 sig figs in our answer, because this portion here is a defined number. Those don't count in our sig figs. So we're going to take our sig figs from our original number. So we're going to have 3 sig figs. So this would be 1.10 times 10 to the 8th milligrams. Alright, in part B, we want to take 68.3 cubic centimeters to meters cubed. None of my metric conversion factors have prepared me for this. But all we have to do is remember what we're really measuring. We're measuring a volume, length times width times height. So if I take what I know, the 68.3 cubic centimeters, and I want to make sure that my centimeters cancels, and I want meters on top. So I want cubic meters on the top, but I'm just going to write meters for now, because I don't know anything about cubic centimeters to cubic meters, but I do know that there's a meter to centimeter conversion. So in 1 meter, there's 100 centimeters. Now, since if I were to do the multiplication here, I'd get centimeters squared times meters. So if I just continuously write out 1 meter over 100 centimeters times 1 meter over 100 centimeters, all 3 of those centimeters cancels out, and I've got meters times meters times meters. That would give me meters cubed. So if I take 68.3 divided by 100 divided by 100 divided by 100, I get 6.83 times 10 to the minus 5 cubic meters. Now, there's a shortcut for this. If you just realize that you take the 68.3 cubic centimeters and you times the 1 meter 100 centimeters, really what I'm doing is I'm cubing everything. So I'd cube the 1 cubed is still 1, cube the meters, I would cube 100, and then I would cube the centimeters. And you actually get the exact same answer in a much quicker form. Alright, in part C we're going to take 7.2 cubic meters and we want to turn it into liters. Again, I don't have a direct conversion from cubic meters to liters, but what I do know is the definition of a liter. 1 liter is equal to 1 cubic decimeter. But again, I don't know cubic decimeters to cubic meters, but I do know what a decimeter to meter conversion is. So we're going to take this again in pieces. So I'm going to take my 7.2 cubic meters times, now I need to cancel out my meters, so I'm going to put meters on the bottom. I want decimeters in order to get to my liters on top. So in 1 meter, there are 10 decimeters. So in 1 cubic meter, there's 10 cubed decimeters cubed. Now, that would give me decimeters cubed, which is actually the same thing as liter, but just for consistency's sake, we'll go ahead and throw in 1 liter is 1 cubic decimeter. And when we do this, we get 7200 liters, not milliliters like I was trying to write. We want liters, so 7,200 liters. And then finally in part D, we're looking at the micrograms to pounds, 28.3 micrograms to pounds. No straight conversion, but I do have a conversion from grams to pounds. So I'm going to take my micrograms, turn it into grams, and then grams to pounds. So I take my 28.3 micrograms times 1 gram is 10 to the 6th micrograms. And then, so my micrograms cancels out. Then I want to go to pounds. So 1 pound is 453.59 grams. And when I do this, I get 6.24 times 10 to the minus 8 pounds. Now notice I've been following the significant figure rules throughout the whole thing, okay? Your calculator would give you a different answer. You just have to make sure that you count the correct number of sig figs, in this case 3 sig figs. So your answer better have 3 sig figs. Alright, here's our first dimensional analysis word problem. In this problem, the normal lead content in human blood is about 0.40 parts per million. And they define what a part per million is. That's 0.40 grams of lead per million grams of blood. And then they tell you that a value of 0.80 parts per million is considered to be dangerous. And then we're finally getting to really the question. How many grams of lead are contained in 6.0 times 10 to the third grams of blood if the lead content is 0.62 ppm? Now this seems to be kind of a daunting task, but what we need to do is we really need to make sure that we pick out the important information. And the important information actually is how to get parts per million. That's one of them. So that's whatever the mass of grams per million grams of blood. So that's how we get ppms. Then we see that a 0.8 part per million is considered to be dangerous, but it doesn't follow through with anything else in the problem, so I'm going to go ahead and just cross that out. We don't really need it. It's just background information. It's what we would call a red herring, which is an old term for a misleading clue. Now, here's the real information. We have the amount of blood, 6.0 times 10 to the third grams of blood. And we've got the lead content in ppms. So I'm going to write down, I've got 6.0 times 10 to the third grams of blood. And then I've got 0.62 parts per million of lead. Okay, so now I want to make sure I don't have anything with parts per million, but what I do know is that, well, if 0.4 parts per million was 0.4 grams per million grams of blood, then this is equal to 0.62 grams of lead for 1 million grams of blood. Okay, so now I actually have this as a conversion factor. And I can see, if I want to get grams of lead, I'm going to multiply this conversion factor by the mass of blood in the human being. So 6.0 times 10 to the third grams of blood. And grams cancels, and I'm left with grams of lead. And when we do this, we get 3.7 times 10 to the minus 3 grams of lead. So it was a very intimidating looking problem, but it actually turned out to be quite simple. The key is to read the problem, know what information you're given and what information is important. Always write down your given information that's important and give it a name, like grams of blood or ppm of lead. And then use that information to try to determine what you're looking for. In this problem, we're asked to carry out a series of conversions between metric and imperial units, and also some time here. We can see we've got the age of the universe in seconds. So let's take one of these, or each of these at a time, just like we did the other one. So A. In A, we're asked for 70 kilograms, and we want to turn that into pounds. So 70 kilograms to pounds. Well, I take my 70 kilograms, and I know from my conversion factor table that I've got a conversion factor of 2.2 pounds is 1 kilogram. And when I do the math here, I end up with 154 pounds. But that is misleading because we only have one sig fig in our number there. So that's actually kind of stinky. This becomes 200 pounds, following the rules of sig figs. In part B, we want to take 14 billion years and convert that to seconds. Now, a billion is 10 to the 9th, so 14 billion would be written as 1.4 times 10 to the 10th years. And we want to turn that into seconds. So I'm going to take my 1.4 times 10 to the 10th years, and I want to get to seconds. So the problem actually tells us, assume there are 365 days in a year. So I'm going to use that as my conversion factor, 365 days in 1 year. Then, how many seconds are in a day? I don't know off the top of my head, but I do know that there are 24 hours in 1 day. And then I know that there are 60 minutes in 1 hour and 60 seconds in 1 minute. So now, all I have to do is multiply this out, and we get 4.4 times 10 to the 17th seconds. That's a lot of seconds. Alright, in part C, we're going to take the height of Yao Ming, 7 foot 6 inches, and turn that into meters. Now, the way that I would approach this problem is I would turn everything into a unit that I could easily convert to the metric system, in this case, inches. So I'm going to take my 7 feet and convert it into inches. So 7 feet times 12 inches for every 1 foot. And then it's a 7 foot 6 inch, so this is slightly more. So I'm going to go ahead and add 6 inches. This means that I have 90 inches. Okay, so Yao Ming is 90 inches tall. So I'm going to take that 90 inches times 2.54 centimeters for every 1 inch, and then convert the centimeters into meters. So 1 meter is 100 centimeters. And what I'm going to get is 2.3 meters. Now, significant figures on this are a little tough because it really should only be one significant figure from the 90 inches. So really we should call this 2 meters. Alright, and finally, we're going to take 88.6 cubic meters and turn that into liters. Now we did a problem very similar to this, so 88.6 meters cubed times, well, we know that a liter is a decimeter cubed, so 10 cubed decimeters cubed for every 1 cubed meter cubed. And then times 1 liter is 1 cubic decimeter. And in this case, we have 886 followed by 20 liters. So 88,600 liters. Problem 83 tells us that a 1 milliliter volume of seawater contains about 4 times 10 to the minus 12 grams of gold. And the total volume of ocean water is estimated to be about 1.5 times 10 to the 21st liters. And we want to calculate how much gold in grams is present in the seawater and the worth of the gold in dollars. And they tell us to see problem 1.82. And then, with so much gold out there, why hasn't someone become rich by mining gold from the ocean? So your first clue is that there should be a lot of gold in the ocean, just from the problem. So, let's take what we know. 1.0 milliliters of seawater contains 4.0 times 10 to the minus 12 grams of gold. And we know that the volume of the ocean is equal to 1.5, not 4, 1.5 times 10 to the 21st liters. So we want to know what is the mass of the gold in the ocean, and also what is the price, so the dollars of gold. So the first thing I want to do is, I see that I've got 1 milliliter contains 4 times 10 to the minus 12 grams. That basically tells me that it's a concentration, kind of like density. So if I want the grams of gold will be on top, and I will divide by, for every 1.0 milliliters of water. So I'm going to take my 1.5 times 10 to the 21 liters, and I'm going to convert that to milliliters because I got to cancel out the milliliters there. So 1,000 milliliters is 1 liter times my concentration here, 4.0 times 10 to the minus 12 grams of gold for every 1.0 milliliters. And when I do this, I end up with 6.0 times 10 to the 12th grams of gold. That is a lot of gold. And I mean a lot of gold. Let's see how much money that is. So, they tell us to take a look at problem 82. And in problem 82, they tell us that the price of gold is $948 for every ounce. So I've got a mass of gold, 6.0 times 10 to the 12th grams of gold, and I need to turn that into ounces. I don't have a direct conversion from grams to ounces, but I convert grams to pounds. So if I put 1 pound on top and the 453.59 grams on the bottom, and then I can convert pounds to ounces. There are 16 ounces for every 1 pound. And then just multiply by the price, $948 per ounce. And when we do this, we see that the value of all the gold in the ocean is 2.0 times 10 to the 14th dollars. So why hasn't anybody become rich from mining gold from the ocean? Because in every single milliliter of seawater, there's just not enough gold. It would cost too much money to refine it than you would get back making it. Alright, this problem is a good example of a problem where you're going to use multiple problem-solving techniques in order to determine the answer. So it says an aluminum cylinder is 10.0 centimeters in length and has a radius of 0.25 centimeters. If the mass of a single aluminum atom is 4.48 times 10 to the minus 23 grams, calculate the number of aluminum atoms present in the cylinder. They also tell us the density of aluminum is 2.70 grams per cubic centimeter. So, always write down what do you know, what do you not know. So we know that the mass of an aluminum atom is equal to 4.48 times 10 to the minus 23 grams. They also tell us that the density of aluminum is equal to 2.7 grams per cubic centimeter, and we want to find out the number of aluminum atoms. And then here's the second part of the problem solving technique that I think is important. Sometimes it's good to draw a picture. So they tell us we have a cylinder. So a cylinder of height equaling 10.0 centimeters, and then the radius here is 0.25 centimeters. Now, you're going to have to call back from geometry to find the volume of that cylinder, because we've got density. Density times volume gives us mass. We have the mass of an aluminum atom in grams per atom. So I can calculate the number of atoms. So, if you don't remember the equation for the volume of a cylinder, the volume of a cylinder is equal to pi r squared h. In other words, the area of the circle times the height. So we can go ahead and plug in our numbers to get the volume of the cylinder. So the volume is equal to 3.14 pi times 0.25 centimeters squared times 10.0 centimeters. And when we do this, we end up with a volume equaling 1.9625 cubic centimeters. It's important to note at this point, do not round to significant figures, because you're not done with the problem. When you do a problem, the only time you round your significant figures is at the very end. So don't round that number. We're going to carry that number through the rest of the problem. So I'm going to take the volume, 1.9625 cubic centimeters, and I'm going to multiply that by the density, 2.70 grams per cubic centimeter, and this will give me the mass of that cylinder. And the mass of that cylinder ends up being 5.29875 grams. Then I take that number and can go ahead and convert to aluminum atoms. So 5.29875 grams times one aluminum atom had a mass of 4.48 times 10 to the minus 23 grams. And so when I do this, I end up with 1.1827 times 10 to the 23rd atoms. Or, following significant figures, when we round at the end here to two significant figures, because we had the 0.25, we have 1.2 times 10 to the 23rd atoms. Okay? So we did all that piecemeal, but we could combine this into one step. Since we know that volume times density gives us mass, then I can just actually plug in pi r squared h times density times one aluminum atom is 4.48 times 10 to the minus 23 grams. And when I do this, guess what I get? The exact same number. So, in this case, by plugging everything into the formula, I wouldn't have to worry about rounding any of my digits or making sure that I carried them through like I do if I do it piecemeal. So, it's always nice to go ahead and carry through stuff when you can, because it actually speeds up the calculation time. Because look, all I have to do is now 3.14 times 0.25 squared times 10.0 times 2.70 times 1 over 4.48 times 10 to the minus 23, and I can do the whole problem in one line. instead of the 5 lines it took me to do it piecemeal. Alright, and finally, we have a problem that actually involves chemistry. Tums is a popular remedy for acid indigestion. Typical Tums tablet contains calcium carbonate plus some inert substances. When ingested, it reacts with the gastric juice, hydrochloric acid in the stomach, to give off carbon dioxide gas. When a 1.328 gram tablet reacted with 40.0 milliliters of hydrochloric acid, and they give us the density of 1.140 grams per milliliter, carbon dioxide gas was given off. And the resulting solution weighed 46.699 grams. And they want us to calculate the number of liters of carbon dioxide gas released if its density is 1.8 grams per liter. So, the first thing in any problem is we want to pull out all the relevant information. So, let's start off with a 1.328 gram tablet of Tums. Then we had 40.00 milliliters of hydrochloric acid solution, HCl. They gave us the density of the HCl, and they said that was 1.140 grams per milliliter. And then they said the mass of the solution after the reaction equals 46.699 grams. They give us the density of carbon dioxide, CO2, is equaling 1.81 grams per liter. And they want us to find out how many liters of CO2 was given off. Now, this problem seems to be a lot more complex than the previous problems, but it's not too bad if we break it down. So we've got the mass of the tablet, and we've got the volume of the HCl and the density of the HCl, which means I can find the mass of the HCl, right? And let's see, what else do I know? I know the mass of the solution after the reaction. Now, carbon dioxide is a gas, which means it bubbles off, which means it leaves the solution. So any mass lost from the combination of the tablet and the hydrochloric acid must be the mass of the gas. So, if I have the mass of the gas, using the density of the gas, I can find the volume. So, the total mass of the reaction mixture must equal the total mass after the reaction. This is the law of conservation of matter. Matter is neither created nor destroyed in a chemical reaction. So, whatever you start with, you have to end with. So, let's deal with the reactant side. So, on the reactant side, RCT, reactant side, we've got the mass of the tablet, and we've got the hydrochloric acid. So I'm going to take my 40.00 milliliters of hydrochloric acid times the density, 1.140 grams per liter, and then I'm going to add in the mass of my Tums tablet, so 1.328 grams. That means the mass of my reactants is 46.928 grams. Now, the reactants minus the mass of the solution must equal the mass of the carbon dioxide. That's the law of conservation of matter. So, I take the 46.928 grams minus 46.699 grams, and that gives me 0.229 grams of CO2. Now I'm going to take my 0.229 grams of CO2 and I'm going to multiply by the density. So, or actually divide the density. So 1 liter, because I want liters, the volume of the CO2, 1 liter of CO2 is 1.8181 grams. So dividing by the density there, I get 0.194 liters. So when you take a Tums tablet and put it into acid, it's going to release 0.194 liters of CO2. Alright, so I've shown you a bunch of dimensional analysis problems, and I'm going to share with you some problem-solving tricks. Always read and reread the question so that you know what you're being asked and know what you're being given. And then with any numerical quantity that's important, write them down and give them a name. And make sure to attach units. It's very important that you follow through and write down your units. And anything that you don't know, write that down as well. So give a name to what quantity it is you don't know. And that will also help, so that you know what units you should be in for your final answer. Now, if there are any formulas you need, write down the formulas when they're appropriate. So density is equal to mass over volume, or the volume of a cylinder was pi r squared h. And then make a sketch if necessary to help you visualize the problem. A lot of times when we just read these abstract words, we may not be able to see what is happening. So if you sketch out a problem, and it doesn't have to be artist quality sketch, it can be just a simple stick figure or a really low quality sketch, just as long as it's a visual representation of the problem, it's going to really aid you in solving that problem. Then you're going to use dimensional analysis to make sure your units work out. Know what you have and know what you need. Now, the final couple of pieces we didn't really go about, but it's always a good idea to look at your final answer and see if it makes sense. If you came up with this last problem, if we'd come up with thousands and thousands of liters of carbon dioxide, would that have made sense from one little Tums tablet? No, that wouldn't have made any sense. Or what if we'd come up with very, very little? That probably didn't make sense either. So just ballpark it in your mind. Know what the size of the answer should be about. And then finally, make sure that you follow through and check your significant figures. Okay? Remember, when you're doing significant figures, especially in these complex calculations, PEMDAS. Please excuse my dear Aunt Sally. The order of operations will help you to determine the correct number of sig figs.